okay, of these 100 samples, obviously, I mean, are probabilistic, right? We generate this, I mean, using the sampling technique. So we sample the posterior, and then we sample from the likelihood. So obviously, I mean, because they have this probabilistic nature, so the author think it is reasonable to draw those lines like with like a lighter color, okay? But well, anyway, like if it's not, it doesn't look clear to you enough, well, you can certainly like just run this program on your computer and see the result by yourself. It's probably easier to observe. Okay, so come back to this explanation. Okay, so also the variance seems to be larger for the simulated data than the actual data. So let's take a again, this is probably a little bit more difficult to observe, okay? First, because if we want to observe like the displacement of the mean, okay, that's probably easier because, well, you just look at like the top of the line, okay? That's easier. But if you want to see like, you know, how much deviate, okay, the predicted samples, okay, is from the mean, okay. That's a little bit difficult to observe, but just want you to be just want you to notice what model do we use. We are using Gaussian model, right? Normal Gaussian, right? So when you have a Gaussian model, when you have a normal model, it's a bell shape, right? It always is a bell shape, right? Okay, once you have sampled your sigma and your mu, okay, from the likelihood, okay, and when you draw your data, I mean, into a line, okay, it is going to be a bell shape, right? It is always going to be a bell shape, right? And the original data, okay, well, you have two outliers here. Remember? If you do not look at those outliers, I mean, obviously it's much concentrated. The data is much concentrated to the center, okay. But the generated, you know, mu and sigma, okay, because of the outlier. Because it has to take care of the outliers as well. So the sigma will be slightly larger in order to accommodate the outlier. Okay, this is the, you know, you can see from the fact that, you know, here most of the lines are, you know, much wider here, right? You cannot observe from the top, but you can observe from here. The data, the generated lines are, what should I say, like much wider. It's not as concentrated as the dark line here. Okay, because it is higher here because it has to accommodate these two outliers. Okay, that's I mean why. Okay, it has like a there like a, you know, the variance is, I mean, are larger. Okay, for the simulated data. than the actual one. Okay. So, whether or not, okay, we can say the model is faulty and needs to be changed. Okay. Remember, we can, I mean, even though we can observe these two differences, but those differences are kind of minor, right? I mean, well, it's the mean moved to the right a little bit, and the variance is slightly larger, but I mean, both are not that far away from the actual data. Okay, so as I said, the interpretation of the model and its evaluation is context dependent. What do I mean by context dependent? It depends on the domain expert. Okay, so based on the author's experience, okay, to this research area. Okay, I mean, he said he thinks that this model is reasonable enough representation of the data and useful for most of the analysis. Okay, so so in Bayesian data analysis, okay, you have to work the your model with the domain scientist. Okay, you cannot, or you have to become the domain scientist of that field. Okay, otherwise, like you know, a lot of times when you analyze, when you do certain analysis, like you need like the result is context dependent. When it comes to a situation like that, you need the domain scientist help to see if the result is presentable, if the result is reasonable. Okay, but of course, okay, how about those outliers? Okay, the reason of the displacement of the mean as well as like a slightly larger of the variance, okay, remember, are really caused by those two outliers, right? So what can we do with outliers? Okay, can we deal with those outliers beforehand? Okay, so one objection, okay, I mean, you may have, okay, with this model, with the normal, we assume the model is a normal distribution, okay, it's a Gaussian distribution model, okay, but we have these two data points, okay, and they obviously do not look like Gaussian at all, right? So these two outliers make this normal assumption, I mean, not as natural, okay, as we anticipated. Okay, so what do we do? Okay, so we can one thing we can do, okay, one possible solution, okay, we can remove those outliers. Okay, in statistics, okay, there are rules that allow us to remove outliers. Okay, so or we can even fix the outliers. I mean, if we know exactly what causes those value to be like that. For example, if we can fix the data point. Okay, if we realize they are just a result of bad coding. Okay, I mean, if it comes from a bad coding, I mean, once you fix your program, of course you are able to correct those errors. Okay, or you remove them, as I said. But so this type of research, okay, how do we deal with this like noisy data. Okay, we want to, I mean, when there are too much noise in the data, we want to, make the data set, look more consistent. Okay, this type of research is actually called data cleansing. Okay, cleansing the data, cleaning the data. Okay. This is actually one of the important research topics, okay, because I have a paper on that in the first tier conference, okay. Data cleansing is important stuff. I mean, at that time we were doing like RFID research, okay. I mean, I'm not sure. I mean, because we are talking about like the passive RFID tag, okay, the one that we use for like for example, like your student ID or your credit card, or the one that is on like Yo-Yo car, okay, basically like those are passive RFID tags. When we do some experiments, I mean, there are, several outliers. So how do we model those outliers to get rid of them? Okay, so those are was an interesting question, because back like about 10 years ago, a little bit more than 10 years ago, RFID research was very hot. Okay, so anyway, okay. So here, okay, if you only want some simple rule, okay, to deal with outliers, what do we do? Okay, these are the two rules that we normally use to get rid of outlier. Okay, the first, any data point below 1.5 times of the interquartile range from the lower quartile, or 1.5 times the interquartile range above the upper quartile is an outlier. First, I mean, do you know quartile? No? Okay. It's called, in Chinese, it's called 四分位数. Okay, you know the mode, right? Everybody know the mode, right? 中位数. Okay, so, so say like if this is the distribution of your data, okay, the mode, okay, the 中位数, okay, is normally at the middle, right? Normally at the middle, okay. Or when you can sort your data, okay, according to certain ranks, okay, and the one in the middle will be the mode, right? We know that, right? And then this is like a 1/4. This is 3/4. So this is the first, the what we call by the lower quartile. This is lower quartile. This is what we call upper quartile. Okay. Okay. So the only thing that left unanswered is what is the interquartile range, right? The interquartile range is the size, okay, between your lower quartile and upper quartile. So this is your, this range is called the interquartile. Okay? So if it's like, 1.5 times of the interquartile range, lower than the lower quartile, or 1.5 times interquartile range, higher than the upper quartile, we consider that outlier. Okay, so this is one way to get rid of the outlier. Okay. The second way to get rid of outlier. Okay, these two are not applied simultaneously. You could, but normally we just pick one. Okay, we just pick one. Okay, so any data point below or above 2 times of the standard deviation of the data, okay, we claim them outlier. Okay, the second one is perhaps more commonly used. Okay, to be honest with you. Okay, but both are valid. Both are valid. Okay. So obviously, if you apply one of these two rules, you may be able to get rid of the, it looks like you are able to get rid of these two outliers, because it looks to us like, the mu should be somewhere here, and the standard deviation should not be too far away from it. So let's consider the second rule. Okay, so twice of the size of the